Welcome to section 1.9. This is the last section in chapter 1 that we are covering this year. We are talking about inverses, and so I want to start off today by looking at this intro question, which hopefully then will define for us what an inverse is. We're going to start by graphing our two functions, f and g. Let f be x minus 4, and so if I go down to -4 and plot my y-intercept, since my slope is 1, I just keep going up 1 over 1, and I'll throw a couple of points in. You end up getting then this line. This is f, so I'm going to call this f of x. And then I'm going to switch my color a second, and let's do g of x. G of x is x plus 4, so my y-intercept is positive 4, and my slope is 1, so I go up 1 over 1. Or down 1 and left 1, either way. And then I extend this line. This is g of x. Okay, now as I'm looking at these are two lines, and we're going to talk about what we notice of them going through. I'm going to start, though, with the 4 questions they give you. Let's do f of g of 2. Well, if I start like we did composites yesterday, if I start with g of 2, I plug a 2 in for x, 2 plus 4 is 6, so then I'm taking f of 6, which you plug a 6 in, 6 minus 4 then equals 2. And what you'll notice is we put in a 2 and we got out a 2. That's something special. So let's try another one. Let's try f of g of 7. G of 7 means 7 plus 4 is 11, so f of 11, then if I put an 11 in for the x and f, 11 minus 4 is 7. And again, what you put in is what you get out. One more, I think you can kind of see the pattern though. G of 132, well 132 plus 4 would be then f of 136. And 136 minus 4, if I put it in f, comes back to 132. And again, you'll notice what you put in is what you get out. And so let's do one more in the general composite. If I take f, and where I saw an x, I put parentheses. Inside of it goes g. Well, you'll notice the 4 and the -4 cancel out. So you get an x, which is exactly what you put into the function. What this means is that these two are inverses because, let me write it this way, f of x and g of x are inverses because what you put in is what you get out. Okay, and that's kind of the idea as we're talking about inverses. What you put in is what you get out. What you'll notice in the graph idea is these two are special graphs because it's a reflection over this y equals x line. And if two graphs are inverses, then you can graph the reflection over the y equals x line. And you should get the same graph. So if I took this graph and reflected it over there, over the y equals x, I would get the red graph. And if I took the red graph and reflected over the y equals x, I would get the blue graph. So we're showing it to you in 2 different ways. Algebraically, if you get out what you put in, then it's an inverse. Graphically, if you can take a graph and reflect it over the y equals x line and get the other graph, then those are inverses. Okay, we're going to talk more algebraically today as we go through, but I want you to see the graph as well. The definition of an inverse says that f and g are inverses if the following is true, and 2 things have to happen. 1, the composite of f of g has to get x. So what you put in, you get out. And the second, if I go the other way, g of f of x has to also get me x. What I put in both directions gets me what I got out in both directions. And so this is the idea, and you have to do 2, must do both. In order to show that things are inverses, you have to do both composites. okay? Your book, a lot of the times, instead of saying G, will say F inverse. And it's like an F to the -1 power, and that's how we write inverse. And so going through, sometimes they will say to you, well, do these two things. F inverse composite with F is X, and, I don't want to say or, I want to say and, F composite with its inverse is also going to get you X. And I want you to see both of these notations, because sometimes you'll see the G, sometimes you'll see F inverse. Either way, the composites have to go in both directions. Okay? Now looking at this, because they are inverses, the domain of the inverse, or the domain of G, is the same thing as the range of F. Because they're inverses, the X and the Y values switch. And I think that's something you probably remember from Algebra 2, but the X and the Y values switch, therefore the domain and the range does also. So if the domain of G is the range of F, then the domain of F would also be the range of G. And basically, again, all they're saying is domain and range switch. Okay, and so that's a lot of the background information. This next example is we're going to start verifying. There will be one just like this on the quiz, where we're going to ask you to verify that two functions are inverses. Okay, so let me slide this down a moment. Again, I'll go back here so you're looking at it. This again is on the quiz. Okay, I'm going to start off by graphing it. Let's look at it graphically. And I'm going to graph this first function f, 2x minus 3. So down to 3, and then my slope is up 2 over 1, up 2 over 1. And you might want to pause this at this time and kind of graph it. That's fine. Okay, I'm going to switch my color. And I'm going to graph g is 1/2 x plus 3. And I'm going to distribute this a minute. 1/2 x plus 3 halves. 3 halves is 1.5, so 1.5 is about here. And this says go up 1 and over 2. 1 over 2. And let's see, I'm having a hard time with my pen, but there's the idea. Okay, again, if we're looking though for inverses, we should know that if they are inverses, I could reflect it over this y equals x line. And as you look at this, it seems to look like, yes, these are inverses because of a reflection. However, a graph is never accurate enough to verify. Okay, it's never accurate enough, because you need to algebraically show me that if I do two composites, that they are inverses. So I'm going to go back and do two composites, f of g, and I'm going to do g of f. And the goal of this is to show that if I put in an x, I'm going to end with an x. And if I put in an x in the g function, I'm going to end with an x as my answer. So that's your goal. So I'm going to start my first composite with f, and I'm going to say 2 times, here's where my x was, minus 3. Inside, I'm going to put 1/2 times x plus 3. Okay, and you'll notice these two are multiplications. I can multiply these first if I want. What that ends up getting is 1. So I have an x plus 3 and then a minus 3. And the 3's cancel out, I just get an x. That's a good thing. Okay, let's try the other way. I'm going to start with g. So 1/2, and then inside I'm going to put another parentheses where my x was, plus 3. And inside I'm going to put 2x minus 3. And I'm going to simplify what I can first. Inside I can get rid of the 3's that are opposites. which means I'm left with 1/2 times 2x, and the 1/2 and the 2 ended up canceling, so I'm left with just x. Because I get x both composites, I know that these are inverses. Okay, because I get x with both composites, I know these are inverses. I'm going to change my color here a minute because I'm not a big fan. All right, take a look. We're going to ask you to name 3 points. Now, we have 3 points listed here. And so I just kind of want to talk about what these points are and how they relate to each other. You can pick any points. I'm just going to kind of show you some general ones. 1 point on F is 0, -3. Another point is 1, -1, and then 2, 1. And the question we're trying to get to here is, how do these points relate to the graph of G? Well, if you look in G, there's this point here of -3, 0. And if you look, I have a point of -1, 1. And if I look, I have the point 1, 2. And what you'll notice, and we talked about above, is these switch the x and the y. Therefore, these are inverses. Okay? So this is another way to look at it. This is not a way to prove it. Please keep that in mind. This is not a way to prove it. This is your method for proving. Okay? If you're going to prove something, it's algebraically by using composites, or showing or verifying. Any of those words come back to the algebraic version. Okay? Looking at F and G here on our graph, looking at F and G, how are they related? Well, the graph of F is a reflection of the graph of G over the line y equals x. And that's why we drew in this blue y equals x line, because we wanted to say, listen, don't you see that they reflect over that line? Is F a function? Is this dark purple or blue graph a function? The answer is yes. You have a couple of reasons for saying it. If they talk about a graph, the easiest way to say that it is a function is it passes the VLT, which is the vertical line test. The vertical line test says, basically, I can draw in these vertical lines, and I'm only going to touch my graph once. We'll take a look at G. Is G a function? Is this red graph a function? Again, we're going to say yes, because again, it passes the VLT. Okay? One way you could say that is yes, because by definition of a function, for every x, there is exactly 1 y. Please remember that definition. You could also use this to say why or why not is it a function. Again, that is the definition of a function, so keep that in mind. Okay? Go ahead and flip the page. We're going to do a couple more examples, and then we'll be done. We're going to talk about the vertical and horizontal line test. We already talked about the vertical line test so far. The vertical line test tells us if the original graph f of x is a function. If it passes the vertical line test, and this is exactly what I just said, that for every value of x, there is exactly one value of y. And that is, again, the definition of a function. Let's make that an E. Okay? The horizontal line test will tell us if the inverse is a function. And it's the same idea. Basically, can you draw a horizontal line? And if so, then for every y, there is one x. And again, then you'll have the inverse be a function. If it can pass both VLT and HLT, we call this 1 to 1. What that means is every x goes to a y and every y goes to an x. That's all it's saying. So no matter what, you will only have one an x and y combination. So we're going to give you an example. Y equals, or f of x equals x squared. So we've graphed this many a times. Let's quick put this graph up. And we're going to ask you if it's 1 to 1. So I'm going to do this. Does it pass the VLT? Does it pass the HLT? Okay, if I can say yes to both, then it is a function. It is 1 to 1. Okay, so take a look. Does this pass the horizontal line test? Well, it's a parabola. The answer then is yes. Okay, and I'm sorry, I'm going to make this graph messy a minute. We want to know if it passes the HLT. So can I put in a horizontal line and have it only touch once? The answer is no, because you'll see here it touches twice. So this is not 1 to 1. Okay, because it does not pass the HLT. Again, don't forget, this HLT tells us, is my inverse a function? My inverse on this graph would look something like this. Well, is this, because it's a reflection, don't forget it's that reflection, is this green graph a function? The answer is no, because look at it, won't pass the vertical line test. So what it does is it allows us to determine if the inverse is a function without actually graphing the inverse. Okay, last idea is to find an inverse algebraically. Okay, and you did this in Algebra 2. I just want to cover it one more time to make sure we're set. First, we want to actually look at the original graph and try the HLT. If the graph doesn't have an inverse, then you stop and you say no inverse is possible. Okay, then if you say there's an inverse, we're going to take the f of x, basically, and we're going to replace that with a y. Okay, so instead of f of x, we're going to write y, which I think you're used to doing anyways. Next, we're going to switch x and y, and your book calls it an interchange, but we're going to switch x and y, and then this is the big part, solve for y. One thing in Algebra 2 we didn't, maybe depending on our teacher, didn't make you do is instead of ending your answer in y, we're going to go back and you're going to tell me it's the inverse by putting in the correct notation to say f inverse of x. And so that's the biggest thing. I need to see this, which maybe your Algebra 2 teacher didn't do, but I need to see this notation because that tells me you're telling me that's the inverse. Okay? So we're going to do one example first. If you stick this in your calculator, you end up finding it's a line, therefore a line has an inverse. So what we're going to do is we're going to start by calling this y, and then we're going to switch x and y. So 3 minus 5y all over 7. Now our goal is to get back to the y by itself. So I'm going to multiply both sides by 7. We have 7x equals 3 minus 5y. Subtract 3. 7x minus 3 equals a negative 5y. And I'm going to divide everything by negative 5. Now I divide each because I'd like it in slope-intercept form. Okay, so let me move this up here. Here's what we've got. I'm going to switch the order a minute, but y equals negative 7/5 x, so that's this part, and a negative make a positive 3/5. So we've solved the equation for y. So that's number 3, but your final answer, you have to say to me, okay, Ms. Schmanik, this is my inverse. Negative 7/5 x plus 3/5. Circle it, star it, bold it, whatever you need. This then is your final answer because you have said to me, here is my inverse. And if you don't tell me that this is your inverse, I'm not sure if this is how you rewrote the original or what's going on. So I need you to say that this is your inverse. Okay? The majority of this lesson is Algebra 2 review. We throw in the horizontal line test, which we didn't cover a whole lot in Algebra 2. But please don't forget, if you have questions, concerns, anything like that, that you let me know in class. We're done with Chapter 1. Enjoy.